First off, I want to check, is anybody here from mathematics? No, everybody's from physics or quantum information physics background.
You've got some mathematicians on the Zoom meeting,
Okay,
so
good to know, good to know.
yes, there's
Just my,
Jonathan.
great. So yeah, just I might, there'll be some comments that might be more directed to mathematicians, although mostly I'm not going to have time to go into how things are proved. So here are some references. Does this thing? Yeah, some references. I'm going to be hopefully talking about 3 results, at least I'll summarize them. And they're with different subsets of these collaborators. So these results are part of a research program which is now called General Probabilistic Theories. And what we do in this research program is we take an abstract framework for describing systems. It's a probabilistic framework, so it generalizes the mixed states, completely positive maps, effects, positive operator value measures, formalism of quantum theory. So one of the things we do is we try to characterize quantum theory and classical theory within a much broader class of foil theories, that foil being contrast, it could potentially provide contrast to quantum and classical theory. And we might hope to, through such characterization theorems that characterize the state space and the measurement space transformations possible in quantum information, obtain formulations of quantum theory that are based on principles that might be a little more appealing intuitively or in terms of information or physics than just saying, well, there's a Hilbert space and there's supermission operators, there are observables, et cetera, et cetera. Another thing, so I'm going to present 3 results along these lines today. Another thing people do is they try to understand how the possibility or the impossibility of information processing protocols, cryptographic, computational, how that's connected with geometric properties of the spaces of states, measurements, dynamics, et cetera. And maybe do the same for physical phenomena like thermodynamic behavior, time reversal symmetry. And a little asterisk, when I say we're characterizing quantum theory, that's an idealization. It's quantum theory in terms of just the framework of density matrices, POVMs, CP maps. We're not, well, you can think about complexity theory in this framework, but we're sort of characterizing the situation where we assume we can do all density, we can prepare all density matrices, measure all POVMs, and think about all, let's say in the quantum case, CP maps as possibly realizable. So it's what you do if you're a computer scientist and you want to prove information theoretic security. It's leaving out a lot of meaty physics that you could argue quantum information over the last few decades has aimed at actually being able to do all of this through computationally manipulating systems using physically available Hamiltonians. So I just want to caution you that we're thinking about when we say we characterize or derive quantum theory, it's sort of the information theoretic part of quantum theory. Okay. Some motivations. I don't necessarily want to say that we've succeeded in all these things, but these were at least some of the motivations. And an interesting one is to get an information-based analog for quantum theory of Einstein's principle-based account of special and general relativity. I'll maybe say a little about whether I think this has been successful so far later. Some people think it might help resolve problems with interpreting quantum information, finding new quantum protocols. I'm not really sure that it actually has led to this much progress. New models of complexity, classes, cryptographic primitives, possible new physics. One I didn't put up here, but I like very much is actually that it's produced some beautiful results of interest in themselves as pure mathematics. At least I think so. Okay, the main results I'm going to describe here are 3, and in particular, I'll concentrate on this first one. And so the first one is with Cozmin and John. This is the archive reference. And we derive quantum state space of density matrices, from 3 postulates. The first is homogeneity. And an information theoretic version of that would be to say that the strictly positive states, the states that never have zero probability for any POVM element. No matter what measurement you do, there's always a positive probability of getting each outcome. Obviously the zero POVM element doesn't count. So we say strictly positive states are interconvertible via probabilistically reversible operations. And in quantum theory, these are, of course, the full rank density matrices. Pure state transitivity, we say the pure states, extremal in the convex set of states, are interconvertible via deterministically reversible operations. And finally, we add either a single property of energy observability or the combination of local tomography and non-classicality. And an interesting fact is that these first two get us to a class of systems called Jordan-algebraic systems, which is very close to quantum. And we only need this last, a choice from these last ones in order to get actual complex quantum theory. Okay. Here are the second and third characterizations. We can get quantum state space and actually the space of measurements from spectrality, which says every pure state is a convex mixture of perfectly distinguishable pure states. In quantum theory, obviously, you decompose any density matrix in terms of rank 1 projectors as a convex combination. Strong symmetry, ordered sets of perfectly distinguishable pure states. So decompositions of the identity matrix into rank 1 projectors, or decompositions of at least of projection matrices into rank 1 projectors, are interconvertible via reversible operations. And the reversible operations are, in quantum theory, density matrix goes to unitary times density matrix times unitary dagger adjoint. Those are invertible, and they maintain normalization. Again, these give you Jordan algebraic systems, which I'll tell you what they are. And the same things are needed if you want to get all the way to complex quantum theory. The third also uses homogeneity, and this one's unpublished. And something I'm calling the generalized projection postulate. Every face of the state space is the image of what we call a filter. And that's a generalization of quantum theory. You take the density matrix, you sandwich it between two projection operators. You're projecting onto the space of density matrices with support in the subspace that these projection operators project onto. And that subspace is a face of the state space. In fact, those subspaces, if you give a support, the density matrices with support on a given subspace are all of the faces of the set of convex set of density matrices. Okay. As I mentioned, the first two give Euclidean Jordan algebras, which are already almost quantum theory. And these share most properties with quantum theory. For example, they've got a spectral decomposition, they've got a trace, all kinds of nice properties. Okay, so now I would like to move on to presenting the general probabilistic framework in the abstract, and then I'll tell you a little bit more about what Jordan algebraic systems are, since that's an intermediate target in all these derivations. Then I will state the results a little more fully, and then that will include giving a more detail about how you get from the Jordan algebraic systems to the complex quantum systems. So I'm going to start with this general probabilistic framework by giving some somewhat technical background. So in quantum theory, we're very interested in the cone of positive semi-definite matrices. Primarily, well, for two primary reasons, because the unit trace positive semi-definite matrices are the density matrices, so that's the state space. And also the measurement outcomes, which are represented by POVM, positive operator valued measure elements, are positive operators, so they are elements of this cone. They also have to be below the identity matrix, or the identity operator in the ordering induced by the cone. And that's to ensure that they give probabilities less than 1. So abstractly, what's a cone? You've got a vector space. We're always going to use. I have to stay here to be audible, right?
Be audible most places.
Okay.
There's also a microphone here.
Excellent. Okay. Right. So we'll be dealing with finite dimensional vector spaces. All of this can be generalized to infinite dimensional spaces, but it gets a bit more technical. So a convex cone is a subset that's closed under non-negative linear combinations. And we're interested in regular cones. So they're pointed. They contain no full line. It should span the vector space, because why would we work in this? Why would we want these extra dimensions around? They're never explored. And it should be topologically closed. That's primarily for convenience, because for instance, if you look at the convex set that you get by slicing through this with a normalization functional like the trace, if it's topologically closed, it's going to have extreme points, and you can use Carathéodory's theorem, for instance, to talk about how every point has a convex in the set is a convex combination of extreme points. Very useful stuff. You could, I suppose, if you wanted, get away with just the interior of the set, because after all, you can arbitrarily approximate anything on the boundary by interior elements. And so you could say, oh, operationally, we don't actually need these things, but they're very handy. And actually, the structure of the boundary does tell you a lot about the structure of the interior. Okay, example, of course, we let V, right, I should say the cone makes V into what we call an ordered vector space. X is bigger than or equal to Y if there are differences in the positive cone, just like with regular real numbers, where the positive cone is the positive half line, non-negative half line. Okay, example, V is the Hermitian matrices, the positive cone is the positive semi-definite ones. The dual of a cone is everything in the dual space. So that's the space of functions from the vector space to the underlying scalar field, which is the reals in our case. The dual cone is everything in the dual space that's non-negative when evaluated on anything in the primal cone. You'll see on the next slide why that's important. And we're going to be very interested in affine maps, particularly, well, because they preserve affine combinations, so linear combinations whose coefficients sum to 1, and therefore they preserve convex combinations. And that's important for probabilistic consistency. So if you have a theory about what operations you can do, and there's some information you're missing, well, the outcome of the operation should sort of be the convex combination of what would have happened if you'd had that information, convex combination with the probabilities that describe the missing information. So yes, Nicole.
I'm not used to doing the cone formalism. Why should I think of the positive semi-definite matrices as forming a cone?
Well, I guess I'll give you some reasons later in the talk. I mean, I guess one reason is because when we generalize this to arbitrary convex compact sets as our space of normalized states, we'll be interested in also having the subnormalized states. And the subnormalized states are the states below the normalized states in the cone.
Where does the order?
So the ordering in, well, again, if you have a cone of this nature, then the ordering just comes from the difference of two things being in the cone. So it's not a total ordering. Some things are not comparable. But for example, if we want to talk about POVM elements, we say they're the order interval between the zero matrix and the identity matrix, or the zero operator and the identity operator. So order is a useful concept for saying what the effects are in quantum theory. So that's a little bit of, yes?
They retain if you operate them on something.
I wouldn't say so. No, it's really, it's more related to Well, maybe you'll see a bit in the next slide. It's related to probabilities being positive, for instance, the fact that it's a positive cone. So let me go on in the formalism, and maybe there'll be a lot more instances where cones come up, and maybe it will make more sense. Okay, so I'm just going to run through what we use in this framework. And by the way, if somebody is having trouble hearing on Zoom, please pipe up in the chat, and I think Andrew will see it. Yeah. Okay. So the normalized state space is just some arbitrary convex compact set. For quantum theory, it's a density matrix. Classical theory, probability simplex. Pure states are extremal in the convex set of states. That means you can't express them as non-trivial convex combinations. Quantum theory, those are rank 1 of some combinations, obviously, of other things in the set. Quantum theory, they're rank 1 projectors, and classical theory, obviously, the vertices of the simplex. You can think of this requirement as saying they're states of maximal information. Because if you could express them as a non-trivial convex combination, you could think of that as, well, maybe somebody really prepared one of those other states that it's a convex combination of, and I just don't know. I'm missing some information. But if it's extremal, you cannot think of it that way. So you think of states of maximal information. The unnormalized states, they're the cone, which I like to call V plus, which is the non-negative reals times normalized states. And let's maybe just have a picture. I'm going to take real quantum theories.
That's a wall.
That's a wall. Okay.
There's a board here. And
yeah, the boards probably won't be visible on Zoom.
Unless we can change things.
It's okay. It's okay. I've got a picture on the next slide. So, do I? Yeah, kind of. Okay. So here we go. This would be the state space of a real quantum bit, because it's a 2-dimensional disk. That's the normalized states. You take the cone over it, that's just, an ordinary old ice cream cone. This is in 3D. If we're in 4D, we could take the 3-dimensional block ball and take the cone over that. And that would be kind of like a Lorentz light cone. Of course, in higher dimensions of quantum theory, the state space is not a ball anymore. But so that's one example. And since people were wondering what's the use of having these unnormalized states around, a nice thing about unnormalized states is that if you do quantum dynamics, for instance, and you apply a completely positive map that's trace non-increasing, then you just take the trace of the resulting subnormalized states, and that's the probability that that operation happens. Then you can have an instrument that's made up of a bunch of those operations that adds up to an operation that preserves the trace. So mathematically, it's handy to have these subnormalized states around, because then you just apply maps that give you subnormalized states, and that encodes also the probability of that map happening. Okay, so back to the state and measurement formalism. Said the unnormalized states are a cone. The probabilities are given by effects, and those are affine functionals. Okay, well, they're affine. Yeah, in fact, they're linear functionals in B star, which are also affine. And we want the functionals evaluated on the normalized states to always give you elements in the interval between 0 and 1, and the reals, probabilities. That's equivalent to just saying that the effect has to be between 0 and the unit functional. What's the unit functional? It's the unique functional that evaluates to 1 on everything in this convex compact set. So again, in this picture, yeah, the unit functional, you can think of there being a plane that slices through here. That's the cone in the normalized states, and that plane is the set on which this unit functional takes the value 1. So in quantum theory, that's just the trace, right? That is the normalization function. Okay, now when we're cooking up theories, it's possible that one might want to specify a convex set that's a subset of these legitimate things that give you probabilities. This is sort of anything that mathematically could be considered a reasonable way of getting a probability on states in this set. But you could say my theory rules out some of those. You're going to want to have the unit, whatever effect you have in this smaller set, you're going to want to have the unit minus it because it's got to be part of at least some measurement. And a complete measurement is a set of these effects that adds up to the unit functional. Although I guess I didn't write that down. I guess I did. So an effect valued measure, right? If it's got a discrete or finite set of outcomes, it'll look like this. You can even cook them up with intervals. If you want continuous outcomes. Okay, and so the unnormalized effects are, at least if we take all effects as allowed, they're the dual B star plus of the state cone. And I think I already mentioned strictly positive states. Those for the normalized ones, those would be the interior, the topological interior of the state space. The unnormalized ones, topological interior of the cone. Okay, so any questions about this part so far? I'll give some more pictures that will maybe make it a little more intuitive. So as I mentioned, this is a real quantum bit. Here's a classical bit. We've got maybe the value 0, the value 1, all convex combinations. That's the normalized state space, just this line. The positive quadrant in R2, in other words, R2 plus, that's the positive cone. You do the same thing for a 3-state quantum system. You get the probability complexes triangle, positive orthant is the positive cone, and so forth. Here's kind of a fun one where the convex set of states is a square filled in, obviously. We call it a squit, or some people call it a squit. So has anybody encountered the Pescu and Rohrlich work on stronger correlations than quantum? So violating Bell inequalities by even more than quantum. And think of the state. I think I better have some water. You can think of the states. You can think of a Popescu-Rohrlich correlation setup as a state on a pair of squits. So you have two possible measurements, and the probabilities for the outcome of each one is given by where you are on the side of the square. This is kind of a cute one. It illustrates that you can have complementarity, two incompatible measurements, and in fact, information disturbance trade-off without having an uncertainty principle, because the basic fine-grained measurements, there's just two of them, and each vertex of the square has a definite outcome for both of those measurements. So cute in a lot of ways. And you can use this also for what might be called random access coding or maybe oblivious transfer. If you have one of these, you can encode 2 bits in it in such a way that the receiver can only access 1 bit perfectly. And if you got a hypercube as your state space, you can encode even more bits. Okay. The effect spaces, it's kind of cute. You just take the dual cone, put it at the origin, and then you turn it upside down, you reflect it, and you reflect it through the plane of the normalization functional being 0, I guess. And you move it so its vertex is at the unit functional. And then the constraint that you be in the cone and the upside down cone, that's one of them's telling you probabilities are positive, the other's telling you they're less than 1. And so you get these interesting bodies. I think we'll won't need a lot of that detail, but Okay, so in this framework, we'll need to know about the existence of what I like to call reducible systems. And these are ones in which some of the information encoded in the state space is purely classical. So we say a cone in a vector space is reducible if the space decomposes as a direct sum of two subspaces. That means they intersect only in the zero vector. And every pure state is in one or the other of those direct summands. And obviously, neither of them is trivial. Neither is the zero vector space. Otherwise, we call it irreducible. And so we also say the cone decomposes into its components in those states. And in fact, every finite dimensional regular cone decomposes uniquely up to relabeling into irreducible ones. And every state, every normalized state, for instance, has a convex decomposition into states that are in one or the other of these vector spaces. So these vector spaces are like super selection sectors. There's no coherence between them. If you want to do a measurement and find out which sector you're in was prepared, that's classical information. Right. Oops. Yes. Oops. So, and just to say one more thing about these reducible systems, if you take the one-dimensional GPT state space, which is sort of trivial, it's just the real line with maybe the normalized states being the number one. And you take the direct sum of n of those, you get an n-state classical state space, probability simplex. Okay, we haven't talked about dynamics yet, but that's extremely important, obviously, for information processing and physics. It's just a pretty straightforward generalization of what we do in quantum theory. We have positive maps. Those are linear maps that take the positive cone into itself. The potential deterministic evolutions are positive maps that for any normalized state, preserve the normalization. So if we evaluate the unit on the output state, it's 1 if the input state has normalization 1. In quantum mechanics, those are the trace preserving positive maps. Okay, reversible dynamics are the group, and I like to call it aut omega for automorphisms of the state space omega, of positive maps that take the state space, the normalized state space, onto itself. Not merely into itself, but onto itself. And in quantum theory, that is rho goes to u rho u dagger for unitary u, and also rho goes to rho transpose. Now, we don't use the transpose as a physical map in quantum theory, and that's because it's probabilistically inconsistent when you start talking about composite systems, right? It takes entangled states to states with negative eigenvalues, so that doesn't have a good probabilistic interpretation. What are the potential probabilistic evolutions? Well, as I mentioned, they're positive maps that are trace non-increasing. So u of phi of omega is less than or equal to 1 if u of omega is 1. And in quantum theory, that's the trace non-increasing positive maps. And usually we'll restrict to the CP, completely positive maps. And the nice thing is the probability of evolution is just evaluating the normalization functional on the output state. Okay, an important concept now, which is a bit abstract seeming, but I'll give it an interpretation, is order automorphisms. These are symmetries of the cone of unnormalized states. It's the group, and I call it automorphisms of the cone, of positive maps that take the cone onto itself. Again, not merely into, but onto. What's that in quantum theory? You take the density matrix to A times rho times A dagger, or in fact, any positive semi-definite matrix
to A row A dagger, where A is any non-singular complex matrix. Important that this is non-singular. And again, row goes to row transpose actually is an automorphism also. So single Krauss operator CP maps with that Krauss operator being non-singular. Probabilistically reversible dynamics. Okay, so it's an easy proposition that the normalization non-increasing order automorphisms are exactly the probabilistically reversible dynamics. And we'll say a little bit more about what that means later.
You did not speak so closely to the microphone.
Yes, okay. I'm just worried. I'm worried about people. Well, I'm a little worried about my voice actually, but I'm worried about people who
Thank you.
are
Do whatever you have.
in Zoom. Yeah. Okay, but yeah. I'll just try to not raise my voice to make sure I'm. So let me know if I'm too quiet. Okay, so I guess I should ask any questions about the overall framework before I then go on to the next topic in presenting the results, which is Euclidean Jordan algebras. Okay. So when we're characterizing quantum theory in this framework, it usually happens that we put together a couple of nice principles, and if we're lucky, we get something non-trivial, and it's usually that we get Jordan-algebraic systems. Sometimes we're lucky enough, we've driven enough principles to get straight to point, but often it's Jordan-algebraic systems. And these were actually invented as a possible framework for quantum theory by Pascual Jordan in 1933. Event of 32. So what's a Jordan algebra? It's a real vector space, commutative, but in general not associative bilinear product. And it satisfies this so-called Jordan property. So it's a special case of associativity. And it's abstracting the symmetric product of Hermitian matrices, because those were quantum observables. And Jordan was wondering, well, the regular product of matrices doesn't preserve hermiticity. So maybe we should think about the product that does. AB plus BA over 2. Okay, and early in the theory, a Jordan algebra was called formally real. If the sum of two squares in the algebra being 0, so A squared is just A dot A. That implies the operators themselves are 0. And okay, I've already mentioned pointed cones. I'll leave that for later. In finite dimension, formal reality is the same thing as Euclideanity. And Euclideanity is saying there's an inner product such that A dot B, inner product C, is the same as A, inner product with B dot C. You can think of this saying that the multiplication, Jordan multiplication operator is self-adjoint with respect to this inner product. So Euclidean Jordan algebras have a unit, which we call U. We define the trace as the inner product with the unit. And you might not be surprised to know that in the quantum case, where it's Hermitian matrices, in this product, the unit is indeed the identity matrix. And so the trace is the trace. All right, the positive cone of the Jordan algebra is the squares.
Sorry.
Yeah.
What was the definition of Euclidean?
I mean, it's not terribly important, but it's that you have this inner product such that you can move. If you do the Jordan product on one side, you can move it to the other side.
Right.
Some people call that I don't know, a term sometimes used. They say the product is associative.
So that Jordan algebras are not associated.
Yes, okay.
We're talking about different types.
So sorry, the inner product is sometimes called associative, but that's different from the Jordan product itself being associative. If the Jordan product's associative, it's basically a classical system. And this cone would be the cone over a simplex. Okay. If you have two Jordan algebras or n Jordan algebras, you can make their product. You literally just take the Cartesian product of the sets, and then you do the Jordan product component-wise. Its positive cone is going to be reducible, and that's why this product notion is of interest. So between the products, the relationship is just classical coherence. For example, block diagonal permission matrices. The blocks are going to be, they're each one. It's going to be a product of the Jordan algebras associated with the Hermitian matrices on each block. We call an EJA, Euclidean Jordan-algebra, simple if it has no such product decomposition. Okay, and a cute fact: if we define embedding one GPT in another, by basically saying you can positively map the state space, the states into the states, and the effects into the effects of the other theory, and when you evaluate them in the other theory that you're embedding into, you get back the probabilities of the original theory. Euclidean Jordan algebra is the only unrestricted systems that embed in quantum theory. So that's another way in which they're practically quantum theory, in addition to having a spectral theorem, trace, etc. What we mean by unrestricted systems, again, is that we take all the effects as allowed. Given the normalized state space, all the effects are allowed. Okay. Just a little bit later, Jordan, von Neumann, and Wigner classified the Jordan algebras. And the simple finite dimensional ones are very simple. They're just self-adjoint n by n matrices over the reals, complexes, the quaternions. So you think of it as real complex and quaternionic quantum theory. So-called spin factors, and that's p dimensions plus an additional dimension with this product. Details don't matter. The positive cone is a Lorentz cone with p space dimensions and one time dimensions. And so the base is just going to be a ball, a p-dimensional ball. The term spin factors comes from the fact you can realize them with spin chains that make Clifford algebra. And then there's the exceptional Jordan algebra. That's 3 by 3 self-adjoint octonionic matrices. And again, with these matrix ones, you just take the obvious symmetrized matrix multiplication as your product. And I should mention that the positive cone, in other words, the squares, since you have this spectral theorem, you have a functional calculus, and so the spectrum of a square is the squares of the elements of the spectrum, and so the spectra are always positive. Okay. All right, so we had to talk about the Jordan algebras because that's the intermediate target in all of these characterizations. And you can see you're very close to quantum theory here. These are just real complex and quaternionic quantum theory, 3 by 3 octonionic quantum theory, and then these balls. Okay. All right, now I'm going to talk about the postulate that is used in 2 of these characterizations, and that's homogeneity of a cone, such as the cone of unnormalized states. So we call a cone homogeneous if the group of order automorphisms acts transitively on the interior of the cone. Any 2 things in the interior, I can find an automorphism that takes the first one x to the second one y. It's a non-trivial fact that the connected identity component of the automorphism group acts transitively if the group does. And in the quantum case, what is this connected identity component? It's these single non-singular Krauss operator CP maps. The transpose is not in the identity component. What's the interior? Non-singular positive semi-definite, matrices. And what is an operation that will get you from matrix X to matrix Y? Well, sorry, it's the one that takes any matrix M to sandwiching that matrix between X to the -1/2, and then sandwiching the result between y to the -1/2. If you plug in x, you're going to get y. So quantum cone of positive semi-definite matrices is homogeneous. And it's basically the same thing with the other two matrix Jordan algebras. We just take the Krauss operators from real matrices and quaternionic matrices, respectively. For spin factors, the automorphism group is generated by Lorentz boosts, uniform dilation or shrinking, reflections, and rotations. So basically the Poincaré group. And if you want the automorphisms of normalized states, it's generated by rotations and reflections of the ball, not surprisingly. It's easy to show that homogeneity is preserved under direct sums, and therefore, in particular, the classical cone is homogeneous. Okay, what's an example of a non-Jordan algebraic homogeneous cone? Just so we know that these other postulates we're going to use are not superfluous. The simplest one is this. We just take a 5-dimensional subspace of the 3 by 3 real symmetric matrices, which you could think of as real quantum theory. And the subspace is defined by setting these two matrix elements to 0. We define the cone by the following constraints. We're basically saying that this matrix is positive semi-definite, and the matrix made out of the corners is positive semi-definite. There. The dual cone is all the positive semi-definite matrices in this space of matrix of symmetric matrices. And it can be shown that this is not self-dual. These two constraints. These constraints are not equivalent to overall positive semi-definiteness. And of course, you know, there are other, well, there are many other homogeneous cones. We could do the similar thing, but do this in Hermitian matrices, and you get another homogeneous cone. Well, interesting. I wonder if sorry. I think I missed a slide, and it's time to perhaps. Come back to, well, let's, yeah, we'll see if we need it. Okay, so a theorem by Kocher and Winberg states that every finite-dimensional self-dual homogeneous cone is isomorphic to the positive cone of a Jordan algebra. So our main theorem, at least our first one, is a similar result, but we're going to replace self-duality with what we call pure transitivity of the automorphism group of the normalized state space for some base of the cone. It can be any base, in particular the one with our favored unit functional being 1. Okay, I guess I should define self-duality, so we'll go back. Okay, so the dual cone can always be represented in the primal space, since we're in finite dimension, using an inner product as a set of all vectors having non-negative inner product with everything in the primal cone. And often you will see, in fact, many authors use, for formulating general probabilistic theories, they formulate it in terms of a single vector space and an inner product, and use that inner product to define duality and measurements. I like to be a little more formal and actually talk about the dual cone. So for example, in quantum systems, we use the trace inner product on the Hermitian matrices, and we represent both effects and states by positive semi-definite matrices. Classical systems, maybe we're going to use Rn and the dot product for both states and effects. So if there is a positive definite inner product with respect to which the dual cone coincides with the primal, we call the cone self-dual. And the interesting thing is, not all cones are self-dual. If the cone is isomorphic to its dual, that's a weaker property than self-duality. Remember, I showed you the cone with the square base. Its dual cone also has a square base, but rotated by 45 degrees. And no matter how you tweak the inner product, it's never going to coincide. Generic cones are neither weakly self-dual nor strongly self-dual. Okay, so that's the notion that's used in this theorem of Winberg. And we wondered, can we get rid of this self-duality requirement, which maybe seems a bit, it's a beautiful property mathematically, but maybe a bit hard to interpret, and substitute it with something like this pure transitivity. Okay, so for the mathematicians, I'm going to just state an important fact that really is at the basis of most of the results about homogeneous cones. And that is that a homogeneous cone is self-dual if and only if its automorphism group is reductive. So reductive is basically, you've got, it's almost the same thing as semi-simple, except that it can have an abelian ideal. And if you don't know, I mean, if that doesn't make sense, it's not important here. Okay, so to state our main result a little more formally now, we're going to define pure state transitivity. We say the automorphism group of the normalized states acts transitively on the pure states. We'll say a system has continuous pure state transitivity if the connected identity component acts transitively on pure states. And that's going to mean that not only can you get from any pure state to any other pure state by an automorphism, in other words, a symmetry of the whole state space, but there's a continuous path of symmetries between any two states. So for example, the square state space or the hypercube, that has the permutation group as its automorphism group. The connected component is trivial, it's just the identity. But nevertheless, it acts transitively on the pure states. Whereas a ball, right, the special orthogonal group, which should act transitively. And that's the identity. There's a continuous path of rotations taking you from any point on the sphere to other point on the sphere of pure states. Okay, so our main theorem, a state space with pure transitivity and whose cone of unnormalized states is homogeneous, is the state space of a product of isomorphic simple Jordan algebras. So you can think of that as, if you like, as a composite of some classical system, which is telling you which factor of the product you're in, and a simple Jordan algebra. If it has continuous pure transitivity, it is the state space of a simple Jordan algebra. These references were important. Okay. And just to give an information focused restatement, I'll focus your attention on this proposition. The automorphism group is precisely the strictly positive multiples of the probabilistically reversible transformations. And we say a transformation is probabilistically reversible, so a transformation being a positive map. If there is another operation, so trace non-increasing positive map, T prime, such that for every initial state, T prime reverses, inverts that, acts as an inverse up to some probability, which might depend on the initial state, although you can show it doesn't. And this probability has to be strictly positive. So if you're doing some information protocol or algorithm, and it's going to be a probabilistic algorithm, this is something that you can succeed in reversing, and you've succeeded, but you're not guaranteed to succeed. But there's always a non-zero probability of succeeding. So it's related to the ability to do things, but not certainty. Okay, so that is the first main result, and it may be the only one we get into more detail on. Let's just motivate the two postulates a bit. So first, the pure transitivity postulates. Well, it's been used in a lot of other characterizations of quantum state space. You might want to focus on the continuous reversibility because you want continuous dynamics in time that are reversible. And maybe it can be motivated by some thermodynamic applications. At least von Neumann used it in his argument that the von Neumann entropy should be the thermodynamic entropy. Another interesting observation is that even the non-continuous version enables teleportation in suitable composite systems. So I haven't talked about composite systems because all these characterizations involve properties of a single system. But you can combine composite systems, generalizing the quantum tensor product of systems. Entanglement, all these concepts generalize. And if you have three systems with suitable state spaces, you could do teleportation protocols in this more abstract setting. So non-continuous, pure state transitivity, plus some other assumptions about having nice entangled states enable you to do teleportation. And I guess a well-known fact of mathematicians is going to be that this implies the existence of a unique state invariant under reversible transformations. You just average over the pure states. So that's, I mean, right. So some motivation for homogeneity, maybe that's a little trickier. But it's saying you could prepare any interior state from any other interior state by an automorphism. Now, every GPT system allows any interior state to be prepared from any interior state, or indeed any state, by a positive map. But that map is basically just throw away the original state, prepare it, the one you want. And that's perfectly good positive map, but it's an entanglement breaking, coherence destroying channel. Automorphisms are sort of the opposite of that. Intuitively, they're going to be maximally entanglement preserving and coherence preserving. And that is borne out when you look at protocols like teleportation, for instance. So preparability of every strictly positive interior state from every other such state by such a process is very unusual in GPTs. And it's important for coherent information processing, such as teleportation, which I mentioned, and also steering. So perhaps I'll close by just describing the connection to steering. So Alex Wills and I and the student Philip Gabler, derived some relations between homogeneity, what Schroeder called steering of marginal states of a bipartite quantum system. And what is steering? It's creating an arbitrary ensemble, probabilistic ensemble, convex combination, for the marginal state of one subsystem of bipartite state, as the state's conditional on the results of a measurement on the other subsystem. You tell me what ensemble you want, I choose POVM, and I conditional on the results of my POVM on my side. The states on your side are states of that ensemble. We also related to the unique purifiability up to local automorphisms postulate, and that is used in some other important GPT work by these folks. We don't actually need local tomography. So this assumed local tomography, in other words, the state of a bipartite system is determined by the correlations between local observables. You don't actually need that for this result. In any theory with universal uniform steering, so that means uniform steering means if you give me system A, I can find another system, it may depend on A, that steers every state in system A. That's the uniformity. And universal just means I can do that for every system in theory. So if we can steer everything uniformly, and the steering system is the same dimension as the steered system, I'd really like to get rid of this. Every irreducible finite dimensional state space in the theory is homogeneous. So that's an example of where a very strong information-related property of quantum theory is a consequence of an abstract property, convex property. And I'll just note that steering is the key to defeating Bennett-Broussard type bit commitment schemes, right? Which are not secure in quantum theory precisely because you can steer. And the idea was to encode the bit in which ensemble you used for a mixed state, and then send that mixed state to Alice. Alice sends the mixed state to Bob to commit, and then Alice is supposed to be able to reveal the bit to Bob, and Bob's supposed to check that, oh, she did use the claimed ensemble. So that's one example of how these abstract geometric properties relate to information processing. And I think I'll stop there. Since the hour's up.
Question.
Yeah, so obviously some people need to go since it's the end of the hour, but thanks for coming and happy to take questions.
Can I just ask a question about actually the last thing that you said? So,
Yes.
I mean, I guess about sort of the connection between steering and bit commitment, but somehow, can you, and I feel like maybe there's been some work on this, can you take sort of the sort of inability to perform bit commitment as like an axiom from which you can derive quantum theory, like at least within some framework? Like, is there a connection here to what you're describing? Or?
That was, yeah, that was like very early on. We wondered about this sort of thing. I mean, I can remember wondering about it as soon as the Myers or Low Chow, especially Low Chow, which is easier to understand.
Right.
Proofs of insecurity of bit commitment and bit commitment impossibility came out. So I think you can. I'm not sure absolutely where it's been done. I mean, it was one of my motivations for so I actually, a lot of us were working on thinking about ideas like this at the same time. And so I actually came up with this postulate independently or not dependently from these guys. And one of my motivations was indeed that it looked like it would enable you to defeat bit commit, because these are the kinds of states that you use. You purify the mixed state in order to make measurements then on purifying system and make any ensemble you want. Now I don't know. So this group did use this particular postulate in derivations of quantum theory. I don't know though whether they used specifically the no bit commitment, like a protocol based. But so there has been a lot of work around this general. You can think of it as deriving quantum theory from the church of the larger Hilbert space, maybe. That's John Sloan used to like to call this property of quantum theory. Yeah. So my feeling is there should be, but yeah, there might be some slippage between this and defeating bit commitment.
Right. Good questions? Okay, I guess if there are no more questions, now let's take our.
Thanks.